Let us take a look at another example. And what we want to do is calculate the capacitance per unit length for a coaxial cable. So far in ECE 140, what you have been doing, let's say you have a source and you have connected it to some circuit. I'm just making a simple circuit, just as if a load. You have connected it to a circuit. You have some wires which would connect this resistance to the source. You have been completely neglecting the wires, and you're basically saying that the circuit is simply behaving like this, right? Any wires you have in the middle, you have been completely neglecting it. And even in EC 106, when we were looking at conductors, we had said that the resistance of the conductors was zero. We have gone to the perfect conductor conditions. However, what do you see? You would be passing current I through these regions. And when you're passing current I, you have a positive charges going one way and you have negative charges going the other way. So you end up creating an electric field between these wires. These two wires are a two-conductor system we have been looking at. So the circuit, these wires are not very straightforward. These wires would have a capacitance between them, and the circuit would be a lot more complex than what you have been analyzing in ECE 140, especially if you go to high frequencies or high speeds. So we will take one specific cable which is highly used, and that is known as a coaxial cable. You should have seen this cable. Your cable TV, for example, would have a coaxial cable. Coming into your modems, normally you have a coaxial cable. Coaxial cable consists of a conductor in the center. Let's call that radius A, and is surrounded by another conductor in a cylindrical form of radius B. The space in the middle is filled with a dielectric, so you can support these conductors. And let's say we have a dielectric of epsilon between the middle. We are going, so in your circuit, for example, when you're applying a circuit, you would have positive charges coming this way on the inner cable, and you would have negative charges coming on the other side, and thus you would end up creating electric fields from the red conductor to the outside conductor. And when there are electric fields between conductors, there would be capacitance associated with it. So we want to calculate what is the capacitance per unit length for a cable like this. Let's see that. Let's set it up. So what Again, I'm just going to tilt it 90 degrees so we can see Gauss law easily. So we have a conductor inside surrounded by another conductor on the outside. I am going to go over a length L and I'm making a Gaussian cylinder over this length L. And let me assume over L we have released charge Q on the inner conductor. So over this length we have charge Q sitting, and charge would be sitting on the outside surface of the inner conductor. And similarly over the same length we have charge minus Q on the outside conductor. I'm calling this to be conductor 1 and outside to be conductor 2. So we can apply Gauss law on this cylinder, and the only thing which matters is the free charge, which is the charge we have released. And I just said, let's assume that over that length L, we have released a charge Q. So applying Gauss law on that cylinder of 2 pi r radius, or 2 pi r circumference, length L, everything we have talked about before is still applicable. The flux on the top and the bottom surfaces is going to be 0 because d and ds are going to be perpendicular to each other. So the flux only exists on the curved surface, and it is going to be 2 pi rl, the surface area, times the d I have there. So my d simply becomes q by 2 pi r l. And E is related to d by the epsilon of the material which is present there. So E becomes d by epsilon, so that becomes q by 2 pi epsilon r l. That would be the electric field between the two conductors. So what we have seen is there is a radial electric field, and if you want to put the vector on it, we can put the vector which becomes q by 2 pi epsilon r l and is radially pointing upwards. Now I have to calculate potential difference between the two conductors 2 to 1. I have to go from one surface of the conductor to the other surface. So let me go on this path. This is the path on which I do the integral. So delta V going from a 2 to 1 would simply be going from a B. You start from B till you reach A, E dr, and thus this would be minus q. I'm just putting all the constants outside the integral, dr by r. And dr by r integral is ln of r, and because I have a negative outside, I can put the b first and then a, and thus the potential difference which I get is q by 2 pi epsilon l, ln of b by a. Since b is greater than a, this term is a positive term, and thus delta v 2 to 1 is positive. I've done things right. I'm going from a negative charge to positive charge. I am walking against the electric field. My potential should be increasing. If I look at my expression at the end, that better be positive. Otherwise, I've done something wrong with the math. So we get Q by 2 pi epsilon L ln B by A. That gives me the potential difference across the two conductors. So to calculate, let me just rewrite it again so we keep it in our sights. To calculate capacitance, all I have to do is delta V 2 to 1, divide them together, and you get 2 pi epsilon L ln B by A. And if I want to calculate capacitance per unit length, then all I have to do is take this length on the other side. So you get C by L. C is the capacitance of that section which I took of length L. Capacitance per unit length becomes 2 pi epsilon ln B by A. Store this in your minds. This coaxial cable, you're going to deal with coaxial cables throughout your life. And we have seen something. We have seen that coaxial cable would have capacitances. So if I consider this coaxial cable and I take small lengths of the coaxial cable, let's say I have length delta Z, very small lengths, and then if I was looking at the circuit of this coaxial cable, I would have these capacitors which would be across the truth levels. So if I was going to represent this cable in a circuit model, at least to what we have learned so far, we would end up getting C delta Z, C delta Z, these capacitors in parallel, where C per unit length, so let's call it per unit length L, that would be given as 2 pi epsilon ln B by A. Later on, when we do magnetic fields, we will realize that besides this capacitance, there is also going to be an inductance on that cable. So this cable is going to behave as if there was an inductor and a capacitor, inductor and a capacitor, inductor and a capacitor circuit like that. And ECE 140, hopefully in the last week, you will see that this is a resonator or an oscillator. that this circuit, when you have an L and a C, it behaves like a resonator. There is a resonance which happens. It's almost like a spring and a mass system. There is an oscillation which would happen there. And the wires you have been dealing with, which in EC 140 you have been totally neglecting, you have been saying, hey, forget these wires, as if they don't even exist. Those wires are actually combinations of these resonators in space. And when you go to high speed circuits, they start playing a very important role. So keep this in mind. Right. That is the capacitance per unit length for a coaxial cable.